What's the statement of the Orbit-Stabilizer Theorem? Let G be a finite group of permutations on a set S. So G itself consists of permutations of S. Note that S itself is not necessarily finite. And if you look in the book, there's an example where they talk about a finite group of permutations on a set S. In fact, it's a set whose points are points in a square. And you're talking about symmetries of a square. That's not finite. The square has infinitely many points. The conclusion is then for any element of that set S, the order of G, the number of elements in G itself, is the product of these two orders, you could call them. Certainly the stabilizer of I in G, as we saw in the first exam, is a subgroup of G. So this really truly is an order of a group here. Actually, the orbit itself, in general, is not a subgroup. The orbit is just a set. S itself is just a set. It doesn't necessarily have a group structure, but we could still put absolute value signs around it to emphasize that's the number of elements in the orbit. What is this useful for? The book emphasizes applications to finding symmetry groups like I think of a soccer ball, for example. Kind of an interesting application, kind of fun, you might say. In real life, the importance of it is hinted at with regard to crystallography, trying to understand the structure of crystals. But to understand a theorem, there's two main things to do. Think about examples and also be able to prove it. Let's work through this example, and then let's also look at the proof. I think this is worth looking at, thinking about the proof of the Orbit-Stabilizer Theorem. Maybe won't do a full proof, but just get the idea across. I have put it on test before, or at least parts of the proof on test before, so it is something that you want to work at trying to understand. But let's do this first, and I'm doing a little bit more than was requested in the book. Let's go ahead and find the orbit and stabilizer, not just for 1, 3, and 5 as in the homework problem, but for 1 through 6. G is a group of permutations, evidently. I mean, they're not proving that. They're not proving G is closed, for example, under function composition of these permutations here, but you're assuming that's the case. On what set? What is S? Evidently, it's the set 1 through 6, which we're not thinking of it as a group. We're just thinking of it as a set of 6 numbers. By the way, the 6 numbers are arbitrary. I could pick 6 other numbers. I could pick 6 objects, 6 people, and think about permutations on any set of 6 objects. And it would be a very similar kind of idea here. So take them one at a time here. Say for I equals 1, what's the orbit of 1? It's all the different things that 1 can get mapped to. Okay, so if you didn't recall what an orbit was, you wanted to look that up. What does 1 get mapped to under all these different permutations? It gets mapped to itself. Under that permutation here, this one maps it to 2. This one maps it to 2. This one maps it to 3. So far we have 1, 2, and 3. This one maps it to 4. That maps it to 3, back to 4. And this one maps it to itself. So it looks like the orbit of 1 is 1, 2, 3, 4. Those are the different things that 1 can get mapped to under these permutations, not 5 or 6. What's the stabilizer of 1? It's going to be a subgroup of G. We saw stabilizers as subgroups. It's this collection of permutations in G that keep 1 fixed, that map it to itself. Certainly that contains the identity. The identity maps every number to itself here. What other permutations map 1 to itself? It looks like there's only one other one, right? Just that one. So this is a subgroup of G of order 2, which makes sense when you look at this permutation. That's a product of 2 disjoint 2 cycles. Its order would be LCM of 2 and 2, which is 2. You square this permutation, so to speak, you're going to get the identity. This is a subgroup of order 2. And the Orbit-Stabilizer Theorem is verified. Number of elements there is 4. Number of elements there is 2. 4 times 2 is the order of G 8, and yes, there's 1, 2, 3, 4, 5, 6, 7, 8 elements in G. For different i's, though, the Orbit-Stabilizer Theorem is still going to work, but the number of elements in these sets could be different. I won't bother rewriting orbits and stabilizer symbols anymore. Let's just put those for headings here. What's the orbit of 2? What can 2 get mapped to? This one maps it to itself. That's the identity. It maps everything to itself. So it can get mapped to itself. It can get mapped to 1 by this one. It gets mapped to 3 by this one. 4 by that one. Back to 1 there. To itself. To 3, to 4. It looks like it's the same as the orbit of 1. But the stabilizer of 2 is different than the stabilizer of 1, because this element here in the stabilizer of 1 doesn't map to itself. But we know if we're going to verify the Orbit-Stabilizer Theorem here, we're going to have 2 elements, certainly one of which is the identity. What's the other one element that maps 2 to itself in this set? Scan through the set. It looks like it's this one here. 5, 6, 1, 3. And once again, that is a permutation that has order 2. And the subgroup has order 2. I equals 3. Quickly scanning, what does 3 get mapped to? Itself. 4, 4, 1, 2, 1, 2. So it looks like it's 1, 2, 3, 4 again. What's the stabilizer? The stabilizer looks like it's the same as the stabilizer of 1. That can happen. Stabilizer of 1, look at that permutation there. That maps 3 to itself, just like it mapped 1 to itself. It did not map 2 to itself. I equals 4. Maps to itself, maps to 3, maps to 1. Looks like we're going to get the same orbit again. To 2, 3, to itself, 1, 2. Yes, same orbit as before. And the stabilizer is going to be the same as the stabilizer of 2. We do get some different kinds of things going on with I equals 5 and 6, I believe. Kind of just by the nature of these disjoint cycles up here. Maybe you noticed. What does 5 get mapped to? It can get mapped to itself. And it can also get mapped to 6, nothing else, right? You look through, scan through all these, it either gets mapped to itself or it gets mapped to 6. The orbit of 5, in fact, is going to be the same as the orbit of 6. And the stabilizer of 5 does include the identity. What else does it include if the Orbit-Stabilizer Theorem is going to be verified? Since these orbits have 2 elements, the stabilizer's got to have 4 elements in both cases. For 5, it'd be that one, this one. Skip that one. Go on to this one. Skip that one, go on to that one. That'll be the stabilizer of 5. And that'll be the same as the stabilizer of 6. I'll just do quotes here to say the stabilizer of 6 is the same thing. Stabilizers are subgroups of G, the group of permutations. Orbits are subsets of S. Something interesting to note here, and this is something I'll emphasize maybe on Friday, is these distinct orbits. You know, these are all the same, and these are all the same. These distinct sets that make up different orbits partition S itself. Notice their intersection is empty, and their union is all of S. That's something that generalizes.